So today, I'm going to tell you about the KPF obliquity survey of small planets. My name is Luke Handley, and I'm starting my third year of graduate school at Caltech. And before I get into things, I want to take a brief moment to thank a lot of my collaborators that make this work possible. So the KPF obliquity survey is much broader than the topic that I'm going to discuss. So there are lots of people attacking these problems from different angles. So I encourage you to reach out to them if you have other questions. So at the start of every talk on this topic, it's obligatory that I show you this a plot like this that basically describes the stellar obliquity angle. So we define this obliquity angle psi as being the degree of misalignment between the orbital angular momentum of a planet and the rotational angular momentum of the host star. And so a large value of psi could be interpreted as a dynamically hot environment, right, where the angular momentum vectors are misaligned from one another. But if they were all relatively aligned, it would probably indicate some kind of quiescent evolution. And we can actually measure this with high-resolution spectroscopy. So for the case of a rotating star, right, there are points on the star's surface that are rotating towards or away from us. In general, these effects cancel out. However, during, for example, an exoplanet transit, a portion of the stellar surface gets occulted by a planet. And as a result, we see a little chunk get bit out of the line profile. And eventually this manifests as a distortion in the radial velocity of the star. And so we can measure this and model it to actually derive the stellar obliquity angle. And that's an equation for the amplitude of this effect, which I'll revisit in a moment. But there's one seminal discovery in this field that's really critical for me to share with you. And this was already touched on a little bit by Kendra earlier today. But if you plot all of the stellar obliquities that we've measured for a large census of giant planets, one of the most seminal relationships that we've discovered is something called the lambda-T effective relationship. So for over a decade, we've known that if you plot as a function of effective temperature, the obliquities that we measure, there is a sharp phase transition at around 6200 Kelvin. And this is interpreted as phase transition in the interior of the stars. And the way we explain this is we say, broadly, that for the coolest stars, there's some kind of tidal mechanism that can act to realign stars relative to their massive planets, while for hot stars, that's probably not effective. And I'm not going to go into too much detail, but that's the broad picture. And what we can take away from this is that for the most massive planets, like the hot Jupiters and above, the obliquities, especially around cool stellar hosts, can actually realign over time. So what that means is that when we observe an aligned obliquity of a massive planet, we don't necessarily know whether we're seeing the results of the true dynamical evolution, or rather seeing the stellar tides obscure the obliquity over time, right? So if you take a really simple estimation of what the timescale of that is, you can kind of fudge the numbers so that it gets out to roughly gigayears, right? So it could be effective. So what's the solution to this? Well, this time scale is very sensitive to the mass of the planet. So if we just observe much smaller planets, for example, Neptune mass planets, which is an order of magnitude lower in mass than Jupiter, this time scale suddenly becomes very long. And so we think that if we observe primarily smaller planets, we can get a better idea of what the true underlying dynamics say as opposed to stellar tides. So why don't we just go and measure hundreds of Neptunes, right? And then just put it to bed. Like, what are the dynamics that are occurring? Well, unfortunately, there are two problems, right? So here, once again, I have this equation for the RM amplitude. And it scales as the ratio of the surface area of the occulting object to the stellar host. And so to put this into context, for stellar binaries, the magnitude of the effect in RV space is like kilometers per second. For massive planets and brown dwarfs, it's like 10 meters per second, 100 meters per second. But for the Neptune and sub-Neptune class of planets, the effect is only at the meter per second or below level, right? So it's really, really hard to detect. And further, stellar brightness is an issue. These types of planets aren't particularly common, right? So the problem is that most of the time when we're going after these Neptune mass planets, they're going to also be around dim stars, which means that stellar brightness plays a role. But given the purpose of this conference, I really want to highlight that Keck plus KPF is a premier instrument for making these types of measurements, right? Because we have the best of both worlds here. First of all, we have stability of RVs, especially over nightly timescales, right? So KPF has demonstrated, down to like the 30 centimeter per second level over the timescales that we're talking about. And further, the massive aperture of Keck combined with the high throughput of KPF makes it so that not only can we collect precise RVs, but we can do so quickly. And this is really important when we're trying to model the RM effect, to make sure that we're not binning over any of the critical shapes. So let's bounce back to what the obliquities look like for massive planets. So if we update this and only consider, Neptune and below mass planets, what do we see? Well, what we see is actually really spectacular, right? Something that we would not have expected just from observing the massive planets. And that's that for small planets, especially, we've really only observed around cooler hosts. But for the small planets, the obliquities bifurcate basically into mostly aligned configurations or really exotic, what we call polar or perpendicular configurations. And so I want to highlight that KPF and Keck are, leading the field and making these observations. And so here's a handful of published observations that are already out there that are really contributing to understanding the statistics. And notice that these are at the meter per second level. But what I want to show you today are some of the earliest results of the obliquity survey, where we've been primarily targeting these small planets. So these are 5 new detections of the Rosendorff-McLaughlin effect for these smaller planets. And I want to highlight, that the uncertainty on these measurements is very low, below the meter per second level for some of the targets. And further, that the amplitudes of these detections are very low, including one at the roughly meter per second level. And so I think we're getting to the point where there's actually enough data to start making statistical claims about what we see. So first of all, one trend that I'm going to point out is that it seems like the Neptunes at the longest periods demonstrate alignment. So we take this sample and we cut it into planets at short orbital periods versus longer orbital periods. We can see that for the shortest planets, this bifurcation remains, while at long orbital periods, it starts to disappear. We see alignment across the board. Next, Neptunes in compact systems are aligned. So if we again split into isolated and compact systems, we see that the polar systems start to disappear. So almost without exception, compact systems are in alignment. This makes sense because they probably quiescently converged and migrated together, and there weren't any significant dynamical perturbations. But speaking of perturbations, if we now split the sample into those that are mostly aligned versus those that have exotic obliquities, what's really interesting is that we don't clearly see a trend towards having confirmed giant companions, which we think are the dynamical perturbers in this system. Now, there's the caveat that, of course, we don't have immensely strong constraints on the companions for all of these. But as part of the survey, I'm collecting RVs that will hopefully allow us to make that claim. Fourth, stellar temperature may not be a factor. This makes sense if we interpret the lambda-T effective relationship as being the result of stellar tides, right? Because the planets are so small, we don't think that there should be any realignment going on. But it'll be really interesting. We're trying to push into this regime now to fully explore the hotter hosts as well. And 5, and I think this is the main and most interesting takeaway from the obliquities of small planets, which is that if we sort our sample into only the isolated, the non-compact Neptune-sized objects with periods less than 7 days, not only do we observe a large number of polar configurations, we actually preferentially observe polar configurations. So when you look at the orbit of a Neptune-class planet in this sample, you're actually more likely to see it orbiting perpendicular relative to its star than you are to see it aligned, which I think is really amazing. And one final trend that I'd like to point out is that I think that the mass ratio axis is a really important one to actually understand what's going on, right? So if we look here at the obliquity distribution for the giant planets around 10 to the -3 mass ratio, we see that there's kind of this uniform blend of obliquities where it's kind of hard to make sense of what we see. There's probably a myriad of different factors that are playing into what we observe. However, if you focus on the area near the mass ratio of 10 to the -4, we see the obliquities start to bifurcate, and in fact, most of the obliquities are actually polar in this mass ratio regime. But something that's even further puzzling is that if we go in further and we observe smaller and smaller planets, it seems like everything starts to shift back down into alignment. And so we can't statistically say for sure whether this is a robust detection, but it's certainly puzzling from a theoretical standpoint. So I didn't have time to touch on any of the dynamics. However, if you're curious about this, I would love to answer questions about it, but I'll put up a few plots from the talk and take questions now.
So thanks, everyone.